Okay, so we're just going to do a bit of revision on Taylor series. So this is the slightly more complicated ones, like if you have a product of things. Like in the tutorial, we had cos x over x. So then you find the Taylor series for cos, and then you divide it by x. Okay, so we'll go through a few of those, and then we'll go through a bit more on that interval of convergence. Okay, so both of that will come up in that assignment. Okay, so for the first one, we have x tan inverse of x, or if you want to write it as x arctan x. Okay, so sometimes this minus 1 confuses some students. They think this is 1 over tan. So if you want to write it as arctan to avoid the confusion, that's fine as well. Okay, so here, like with those previous examples, we've got a product of things. So we're never going to have a product of two different functions that are complicated. So one of the functions will always be like x or x squared or 1 over x, and then the other one will be something that we've done before. Okay, so you won't get something like e to the x arctan x. That's too much. Okay, so the first thing we do is try and find the Taylor series for arctan, and then once that is done, then we multiply by x. Okay, so the first thing to do is find Taylor series for arctan x. Okay, once we've got that, we can multiply the result by x. Now this one we have covered before, but I'll go through it again. So note that the derivative of arctan equals 1 over 1 plus x squared. Okay, that's just something that you need to know with those antiderivatives. So if we integrate both sides, then we get back to arctan. Okay, so it's just undoing that derivative. Now this 1 over 1 plus x squared, we can treat it like an infinite geometric series. So remember that 1 over 1 minus r, that's 1 plus r squared plus dot dot dot. Right? The geometric series where the ratio is r. So here we've got a geometric series, but the ratio r is minus x squared. Okay, because you've got the minus from there, but that's a plus x squared, so you need to put a minus x squared. So here r equals minus x squared. Okay, just so that we get this that plus over there. Okay, so we can write this integral 1 over 1 plus x squared as the integral of that geometric series, which we can write as the sum from k equals 0 to infinity, r to the n, r to the k in this case, but r is minus x squared. So it will be minus x squared to the k, okay, dx. Okay, we can simplify this a little bit and then swap the integral and the sum so that we can integrate each of the terms individually. So here we can write it as the sum, k equals 0 to infinity, minus 1 to the k, so that's just taking the minus out from the minus x squared, we can take that out. Then we have the integral of x to the 2k dx. So I just took the k from the outside and then took it inside. Okay, so x squared to the k is x to the 2k. Okay, now we can integrate this quite easily. So this will be the sum from k equals 0 to infinity minus 1 to the k. Add 1 to the exponent and divide, so it will be x to the 2k plus 1 over 2k plus 1. Okay. And then that left-hand side, remember that integral was our arctan. So that is our arctan x. Okay, but we don't want arctan x. Remember the question said x arctan x. So we just multiply everything by x at the end. So therefore x arctan x. Okay, we just multiply by x, but then the x can go into the sum, and which means we just add 1 to the exponent. So whatever it was, we just plus 1. So we have the sum k equals 0 to infinity minus 1 to the k over 2k plus 1 x to the 2k plus 2. Good. If we were to divide by x, then we would minus 1 from the exponent. Okay. So you'll never have something very complicated in front. It'll be like x squared or x or 1 over x or something. You're just changing the exponent at the end. Okay. Okay, so we've got that. Then if we wanted to find the interval of convergence, we just treat this as a series like we did in the previous chapter, and we check when does it converge. So for these cases, it's always that ratio test. Okay, we covered that last week. So we have the limit, k goes to infinity, absolute value, the k plus 1 term divided by the k term. So k plus 1, that will be minus 1 k plus 1, x to the 2, and then we put the k plus 1 plus 2. Okay, so remember to put your brackets around the k, because from k we go to k plus 1. Okay, so you need the brackets around there. Okay, divided by 2, and again brackets k plus 1, that's all one thing plus 1. Then we need to divide by the k term, but since the k term is a fraction, if you divide by a fraction, you can multiply by the reciprocal. So we can write that as 2k plus 1 over minus 1 to the k, x to the 2k plus 2. Okay, so dividing by the fraction or multiplying by the reciprocal. Okay, we can clean this up a bit. So the minus 1 to the k plus 1 and minus 1 to the k, it will either be minus 1 or 1. Okay, but since we've got those absolute values, it doesn't matter what it is, it's always going to end up being positive, so we can just cancel that. Okay, so if it's minus 1, the absolute value cancels it. If it's 1, it's not doing anything, so we can just get rid of it. Okay, so that will be the limits. K goes to infinity, x to the, now we can expand that out, so it will be x to the 2k times x to the, then we have the 2 from the brackets, so that will be a 2 plus another 2, that will be a 4. Okay, and then we have 2k plus 1 left over there. And then in the bottom, we have 2k plus 2 plus another 1, so it will be 2k plus 3 in the bottom, and then x to the 2k times x squared. Okay, so that's just cleaning that up a bit. Then the x to the 2k at the top, x to the 2k at the bottom, we can just get rid of that. Don't need that. Then x to the 4 at the top, x squared at the bottom, we're going to have an x squared at the top. We can take that out as a constant. And then we have the limits, k goes to infinity. We have 2k plus 1 at the top, and 2k plus 3 at the bottom. Okay. Now with this one, you can do it a number of ways. You can use your L'Hopital's rule, because you got that infinity over infinity, or you can factor out a 2k at the top and the bottom. So here we can write it as x squared, limits k goes to infinity, 2k, and then 1 plus 1 over 2k. And then here we have 2k, 1 plus 3 over 2k. Okay, so that's just factoring out the top and the bottom. The reason I did that is because we can cancel the 2k's, there and there. Now, if we take the limit in this form, that 1 over 2k will be 0, the 3 over 2k will be 0, so it will just be 1 over 1, which is 1. So that will just be a 1, and we're left with the x squared. Okay, now that's our answer for the limit value. Now, if we want this to converge, that answer must be less than 1. Okay, remember with the ratio test, if it's greater than 1, it diverges, less than 1 converges, equal to 1, try something else. So if we want this whole thing to converge, this better be less than 1. Okay. Now, absolute value of x squared, we don't need the absolute value because x squared is positive. So we can just write that as x squared less than 1. And then if you want to write this as an interval, it will be minus 1 less than x less than 1. or if you draw a little picture here, I can do that better. So like if you got your parabola, here's 1, and we have minus 1 to 1. Okay, so it's between that. Okay, so this is our interval of convergence. Okay, any questions on that? Okay, so we've got the Taylor series, and then this is where it converges. If you're within this part, it converges for those x values. If you're outside that part, then it goes off to infinity. Okay. At the end of the lecture, I'll show you the graphs, and you can see where it converges. Okay, number 2, we have sine squared x. Now, for this one, you might think that you need to do the derivative and then the second derivative and so on. But if you try it with this, it's going to be a bit messy. Because you can substitute 0 here, that's fine. But then when you do the first derivative, it will be 2 sine x cos x. That's fine still. When you have to do the derivative again, you got the product rule. And then it gets more and more complicated. So you can do it that way. Or we can write this as 1/2 1 minus cos 2x. Remember those double angle formulas and so on? So here we can write it as 1/2 minus 1/2 cos 2x. Now that 1/2 is a constant, cos, we know what the Taylor series for that is. Right? We did that a while back. So instead of finding the Taylor series for sine squared, we can find the Taylor series for cos, and then just substitute. So recall, if we have cos t, we can write that as the sum k equals 0 to infinity minus 1 to the k, 2k factorial, because you're always looking at the even terms, so it must be 2k, and then x to the 2k, again, we want all those even terms. Sorry, not x, that should be a t. That's a t. Okay, so cos of t, and then we have t on the other side. So that's cos of t. If we want cos of 2x, we can just substitute 2x. So cos of 2x, exactly the same, k equals 0 to infinity, minus 1 to the k over 2k factorial, 2x to the 2k. So I've just substituted. Okay. If that was like x squared, you just put in your x squared. If it was x cubed, you put in your x cubed. Okay. So here we can fix this up. So this will be cos 2x. That's the sum from k equals 0 to infinity minus 1 to the k. The 2 to the 2k we can take out. So it will be 2 to the 2k over 2k factorial x to the 2k. Okay, so that's for the cos 2x. But here we want 1/2 minus 1/2 cos 2x. So we just take the series and then we substitute it. So sine squared x, that's 1/2 minus 1/2 cos 2x, but we've got that already. So this will be 1/2 minus 1/2, the sum from k equals 0 to infinity, minus 1 to the k, sorry, just copy that, minus 1 to the k, 2 to the 2k over 2k factorial x to the 2k. Now you can leave it like this, that's fine, but if we substitute k equals 0 into that, we get 1/2. Okay, you can check that. So we have 1/2 minus, and then the first term from the series is 1/2. So 1/2 minus 1/2, that cancels. So what we can do is start this from k equals 1, since the k equals 0 term cancels. But you don't need to do this, it's just, it's optional. So we can write it as minus the sum from k equals 1, because the k equals 0 cancels, 1 to infinity. Then we have minus 1 to the k, 2 to the 2k, over 2k factorial x to the 2k. So if you can simplify it like that, that's fine, but this previous line here, that's fine. Okay, if you leave it like that. Okay, and if we want to find the, sorry, there's a half in front. Okay, so the half here up in front there. So if you want to find the interval of convergence, we do the same thing as before. So you do the ratio test with the k plus 1 term and the k term. So let's go through that. So we find the limits. K goes to infinity. We look at the k plus 1 term and then divide it by the k term. So that will be minus 1 to the k, to k plus 1, 2 to the 2k, x to the 2k plus 1, in brackets like that, all over 2 times 2 times k plus 1 factorial. So wherever there was the k, I'll put the k plus 1. Okay, then we divide by the k term or we multiply by the reciprocal. So that will be 2k factorial over minus 1 to the k, 2 to the 2k, x to the 2k. Okay. Again, so we just divided by the k term or we multiply by the reciprocal. So very similar to what we did before. The minus 1 to the k plus 1, that can go. Minus 1 to the k, that can go. So this will be limit. K goes to infinity. 2 to the 2k, and at the top here. And then 2 to the 2k at the bottom here. That's supposed to be... at the top here, that is 2 to the 2k plus 1 minus 1. Okay, so we can separate that out. So that's 2 to the 2k plus 2 minus 1, so plus 1. And then 2k factorial, we can leave that alone. Okay, and then in the bottom, we have 2k plus 2 factorial. So 2k plus 2 factorial. We'll get to that later. Yeah. Here? Yeah, we're getting there. That's the next thing I'm going to write down. Yeah, so I'm just dealing with the factorial part, and then we'll put the x part. Okay, and then the 2 to the 2k at the bottom. Okay, and then the x part. So that will be x to the 2k plus 2, and then x to the 2k. Yeah, I wanted to do it later so that we can cancel them on top of each other. Okay, yeah.
Yes, sir, I do not understand that part where we have our 2k factorial. How did we do that?
This top part, the top one. So that 2k factorial came from this denominator here. So the denominator there became the numerator when we did that division. Okay. Okay. So now, 2 to the 2k plus 1 at the top, 2 to the 2k at the bottom. We can cancel the 2 to the 2k part. So that will be limit k goes to infinity. We left with the 2 at the top, 2k factorial, x to the 2k times x squared. And then in the bottom here, what we want to do is write that 2k plus 2 factorial with something like 2k factorial, so they can cancel. So here we can write it as 2k plus 2, 2k plus 1, 2k factorial. Okay, so I just wrote it in that descending part. So if you have like 4 factorial, you can write it as 4 times 3 times 2 factorial. Okay, so that plus 2, there was a plus 2, then it became a plus 1, then it became a plus 0. But that's nice because 2k factorial at the top and the bottom, they can cancel. Okay, and then we have the 2 to the 2k, x to the 2k, sorry. So the factorials can go, the x to the 2k can go, and then we're left with this absolute value x squared. We can take that out. then we have the limits, k goes to infinity, 2 over 2k plus 2, 2k plus 1. Now you can multiply this out if you want to, but notice we're going to end up with the k squared in the bottom, and we just have a 2 at the top. So if k goes to infinity, it goes to 0. Okay, so you don't need to multiply it out. If you can see it goes to 0, then that's fine. So this goes to 0, which means the whole thing goes to 0. Since it's always 0, it means it's always less than 1. So it always converges. So always 0, always less than 1. So finally, it always converges. Okay, which is what we expect with something like sine. Remember, we showed cos always converges. So sine, that also always converges. Sine squared would also always converge because we showed at the top that it's just a cos. It's just a cos. So if cos always converges, then that converges, and so does sine squared. Okay, but this is just to show fully. Okay, any questions with this one? Okay, next one. Number 3. So here we have sine hyperbolic x squared. Okay, whenever you have these compositions of functions, so on the outside we have sine hyperbolic, on the inside we have x squared, instead of treating it all together, what we can do is first look at sine hyperbolic t. Okay, so we find the Taylor series for sine hyperbolic t, and then right at the end we can substitute t equals x squared. Okay, so you don't have to do everything at once, you can do it in parts. Okay, so let's look at sine hyperbolic t. If we look at the derivative of sine hyperbolic t, that will be cos hyperbolic t. And the derivative of cos hyperbolic t is sine hyperbolic t. So let's write that down. d by dt of sine hyperbolic is cos hyperbolic, and d by dt of cos hyperbolic is sine hyperbolic. Okay, so they just turn into each other when you do those derivatives. Okay, so what happens when we substitute 0? So sine hyperbolic at 0, that's going to be 0. And cos hyperbolic at 0, that's going to be 1. Okay, so let's look at a few of the derivatives as we go through and see what happens. Sorry? No. So for the trig functions, it goes plus, minus, plus, minus. For this one, it always stays like that. So if you want to show it fully, you can do it like this. So sine hyperbolic, that's e to the t minus e to the minus t over 2. And you can check, if you take the derivative, you end up with the cos hyperbolic, which you can write like this. So it's e to the t plus e to the minus t over 2. So you can just check with this. Okay. Or you can just memorize that they turn into each other. Okay, so this is just something on the side. Okay, if you want to check the derivatives. Okay, so let's say f of t is sine hyperbolic t. Okay, and then f at 0, that's going to be 0, okay, from above. F prime, that's going to be cos hyperbolic t. So f prime at 0, that will be 1. F double prime at t, that will be sine hyperbolic t. F double prime at 0 will then be 0. Okay. You can check a few more. You'll see that all of the ones with the first derivative, the third derivative, the fifth derivative, all of those will be 1. All of the even ones, that will be 0. So we're only looking for odd terms. Only looking for odd terms. Okay, so if we want to write it in terms of k, and we want only the odd terms, we can use 2k plus 1, because that's always odd. So sine hyperbolic t, that will be the sum from k equals 0 to infinity, 1 over 2k plus 1 factorial, because we only want odd terms, and then that will be t to the 2k plus 1. Okay, but that's t. We wanted sine hyperbolic x squared, so we can put in the x squared now. Yeah.
Why is 2k plus 1? And still 2 is even and plus.
So the 2k will always be even, and then 1 after an even number is always odd. Yeah, yeah, yeah. Yeah, and then we start from 0. So if you put in 0, you get 1. If you put k equals 1, you get 3, then 5, then 7, and so on. Okay, so that will be the sum from k equals 0 to infinity, 1 over 2k plus 1 factorial. And then here we can put in our x squared to the 2k plus 1. Okay, so that will be your sine hyperbolic squared. Okay, question? Yeah. Yes. Yeah, that's it. That's what you have to do. Yeah, it's easy stuff. You don't have to do anything more than that. No, it's not so bad. So once you've done a few, like with the cos and the sine and the e to the x, if you've done it before, you don't have to redo it. So like here, if you remember that sine hyperbolic t looks like that, if I ask you for sine hyperbolic x cubed, you just put in x cubed. Or if I ask you for sine hyperbolic 1 over x, then you just put in 1 over x. You don't have to redo everything. Okay. Yes?
So since I know the states this for sine hyperbolic t, would it be penalty if I just write it like this without showing the step and then substitute the step?
Yeah, that's fine. You just put it in.
Without showing how I get it to...
Yeah, if you write the series down and it's correct, you get the marks. And no, you got it right. I'm not going to... If you know like it's 100% right, then you can just put the answer down. If you're unsure and you want to check, then you can put the rest. But like, so the way the marking works is like if it's wrong, then I look for part marks and you're working. But if it's right, I'm just going to tick and then move on. Yeah, same goes for the other questions like cos 1 over x. If you want to start from the beginning because you're unsure, that's fine, you'll get part marks. If you just put down 1 over 2k factorial 1 over x to the 2k, it's right, I'll put a tick, move on. Okay. Yeah, so like in the tutorials, if you see a question there and you think, oh, that might come up, like e to the x, right? That's 1 over k factorial x to the k. If you memorize that and you write it down, that's fine. You don't have to redo everything every time. Okay, so that's sine hyperbolic. Then the next one is number 4. So this is f of x equals 1 over 1 minus x squared. Okay, so, yeah.
Will I be right or correct if I add 1 on the last question to get the convergence of my sine hyperbolic x squared?
For the convergence. So for the convergence, you replace the k with k plus 1. So that's for that term. So it will be, we can do it here. So we have the limits, k goes to infinity. So that will be x squared to that. So it will be x to the x squared to the 2, and then k plus 1 in brackets, plus 1. So it will be 2k plus 2 plus 1. So it will be plus 3 at the end. Over, this will be 2, and then k plus 1, and then plus 1. Okay, then we divide by the fraction or multiply by the reciprocal. So we can write that as 2k plus 1 factorial over x squared to the 2k plus 1. Okay, so a lot of brackets here, but we'll take it a step at a time. So it will be the limit, k goes to infinity, x squared to the 2k plus 3. Okay, so it will be x to the 2k plus 3. Okay, so we'll take it a step at a time. So that upper exponent, that will be 2k plus 2 plus 1, so 2k plus 3. We'll leave it like that. And then when we multiply it inside, we need to multiply everything by 2. But we'll do that in the next step. And then we have 2k plus 1 factorial. And then here, this will be 2k plus 2 plus 1, so 2k plus 3. All of that factorial. And then here will be x to the 2k plus 1. Okay, so now we can distribute everything. So this will be limit k goes to infinity, x to the 4k, and then x to the 6. Yeah. Okay, and then 2k plus 1 factorial, we can leave it like that. 2k plus 3 factorial, we want it to be like that 2k plus 1. So we'll start off with 2k plus 3, and then 2k plus 2, and then 2k plus 1 factorial. You can stop when it matches the numerator, and then that can cancel. Okay, and then we're left with the x to the 4k, and then the x squared. Okay, the factorials, they can go, the 4k, that can go x to the 6 over x squared, that will be x to the 4. We can take that out. Then we have the limit, k goes to infinity. We're left with the 1 at the top, and then at the bottom, 2k plus 3, 2k plus 2. That's similar to what we had before. Again, you don't need to multiply it out. We know the bottom will be something k squared. So if the bottom bit is k squared, if k goes to infinity, 1 over infinity, that's 0. So all of that, that's just 0. Okay, so everything is 0, which is always less than 1, so it always converges. Okay, so we don't have issues with any particular interval. Okay, it is end of the lecture time. Do you have to go somewhere? You're all good. Okay, so let's finish this last one. Okay, so we've got this function here. Now, there's no nice tricks for this. We can't write it as a series, like that 1 over 1 minus x. So with this one, we have to go back to the original, those original steps. So we write it as 1 minus x to the minus 2, and then we have to take those derivatives. Okay, so let's write it out neatly. So f of x, that's 1 minus x to the minus 2. F at 0, that's just going to be 1. Okay, then we take the derivative. So that will be minus 2 times all of that. But then with the chain rule, you're multiplying by another minus 1. So it'll be minus 2 times minus 1, so we can just put it 2. 1 minus x to the minus 3. Okay, and then f prime at 0, that will just be at 2. Okay. Now we do it again and try to look for a pattern. So f double prime. Now we're going to have 2 times minus 3, and then because of the chain rule times another minus 1. So it will be a 6, but I'm going to write it as 2 times 3. So 2 times 3, 1 minus x to the minus 4. So f double prime at 0, I'm going to leave that as 2 times 3. Okay, you'll see in the next step where the pattern goes. So let's do the derivative again. So f 1, 2, 3, so 3 derivatives. It will be 2 times 3 times minus 4. And then with the chain rule, we get another minus 1. So it will be 2 times 3 times 4. 2 times 3 times 4. 1 minus x to the minus 5. And then f 1, 2, 3 at 0 will just be 2 times 3 times 4. Okay, so what we can do now is this 2 we can write as 1 times 2. The 2 times 3 we can write as 1 times 2 times 3. And 2 times 3 times 4, that will be 1 times 2 times 3 times 4. So I'm sure you see the pattern now. It's a factorial. Yeah. So the third derivative gives us 4 factorial. The second derivative gives us 3 factorial. The first derivative gives us 2. So it's always one more. So if we look at the kth derivative at 0, it's always the next one factorial. So the third derivative was 4 factorial. So the kth derivative will be k plus 1 factorial. Okay. So first, just a few terms, and you can see what the pattern is. Okay, it will be quite clear like that. Okay, so we've got this. Now we can write the Taylor series. So that will be the sum k equals 0 to infinity, the kth derivative at 0 over k factorial x to the k. So that's just from that definition way back. Okay, so we can substitute this. So that will be the sum k equals 0 to infinity, k plus 1. I'm going to write the k plus 1 factorial as k plus 1 times k factorial. So it cancels, yeah, over k factorial. So now that cancels. Okay, again, we still have that x to the k. Okay, so cancel, cancel. So we get the sum from k equals 0 to infinity, k plus 1, x to the k. Okay. So this one over here, if you didn't cancel it, that's fine. If you write the top part as k plus 1 factorial and the bottom part as k factorial, that's fine. But you could cancel it and make it simpler. Okay. Maybe if there's like follow-up questions, it will help if it's simpler. But it's not needed. Okay, let's see where this converges, and then we'll end the lecture there. So we want the limit as k goes to infinity. The k plus 1 term, so if it's k plus 1, we add 1, so k plus 2. X to the k plus 1, divided by the k term, so that will just be k plus 1, x to the k. Okay, so this one's quite easy to do. So we have the limit, k goes to infinity. X to the k plus 1, we can write it as x to the k times x. So the x to the k's will cancel. So we can have a x there, and then k plus 2 over k plus 1. Okay, we can take the x out. Then we have the limits, k goes to infinity. Here, again, we've got that problem of infinity over infinity. We can factor out a k. So we'll have k 1 plus 2 over k, and then k 1 plus 1 over k. Okay, so we get rid of that, we get rid of that. So now if k goes to infinity, the 2 over k, that will be 0. 1 over k, that will be 0. 1 over 1 is 1. So that's the absolute value of x. Now, for this to converge, we want the limit value to be less than 1. Yeah, so less than 1. So if absolute value of x is less than 1, then the interval is from minus 1 to 1. Okay, easy stuff. Okay, so if we just had x here, I'll get your question now. So if we just had x, it will be from minus 1 to 1. Over here, if I replace this with 2x, for example, or 3x or something, then when we do this limit here, this x might be different. So it could be absolute value of 3x is less than 1. Okay, then you have to do a little bit more work. But for this one, it's quite easy. Yeah? Sure. That was the first one. Or the second one. This one.
Yes, this one.
Yeah.
One here is x squared into less than 1.
Yeah.
Minus 1 is less than x instead of x squared.
Oh, so I wrote it instead of the single x squared being less than 1. I wrote it as an interval with just x. So we don't want to know what x squared is. We want the x values.
So we want to grow it right?
Yeah, so yeah, this graph is just to show you what it looks like. So if we got the parabola, if y equals 1, that's just the horizontal line. If we want to know where it's less than 1, then it's going to be from here minus 1 to here at 1. That's a quick way. If you want to do it the long way, we can have x squared is less than 1. So x squared minus 1 is less than 0. Then we can factor this as x minus 1, x plus 1 less than 0. So this is the long way, like from high school stuff. Then here we write the number line, minus 1 and 1, and then you look for a value, value here, value here, value here. So it'll be like this, and then we see where is it less than 0, it'll be here, and then that will be minus 1 less than x less than 1. That's the long, long way. Okay. Or you can draw the picture, and then you see.
How can we do x squared less than 1 is the same as x is 70 as x is 60.
Yeah, that's right, yeah.
Oh.
Yeah. So you could have also written it like minus 1, 1. You can write it like that as well. Yeah. Yeah. Yeah, you could. For those ones, it's a little bit more difficult. So I'll just write that here. It's a bit too much work to do. But if we have arc sine, we can take the derivative. So d by dx of sine inverse x. So that will be 1 over square roots 1 minus x squared. Okay, we take the derivative, and then now we can write this as 1 minus x squared to the minus 1/2. And then once we've got here, we can then find the second derivative and the third derivative and so on. But that's quite a bit of work to do. Okay. But the arctan, that one's easy to do because we can write it as that series. But this one, you have to do the whole long method. Yeah. So you won't get something like this. That's too much. I could ask you to find the first 3 terms. So you say arc sine at 0, then you find the first derivative and the second derivative. So then now you're only looking at 3 terms. But I won't say find like all of them. Okay. Any other questions? Sorry? Oh, good. Okay, sure. Okay, so that will be it for today then.